Next one in the quantum mechanics point of view. So as in the molecular orbital theory and some other concepts, valency band theory, etc. And another one more fundamental one, it may be this, but sometimes in the examination point of view, questions will be there. The molecular orbital theory case, molecular orbital theory point of view, MOT case. We have seen some of the points. That means based on the electrons, electrons can be filled in the molecular orbitals. Electrons can be filled in the molecular orbitals. Bond order is there. Bond order, right? As well as the bond length, and whether we can say that paramagnetic and diamagnetic based on this molecular orbital theory also. Right? Some of the homodiatomic molecules and heterodiatomic molecules. Homo as well as heterodiatomic molecules case. Listen. So according to the molecular orbital theory, so we can, if it is atomic orbitals, it may be takes place, suppose atomic orbitals of the different atoms, or it may be the same atoms. Same atoms also it may be takes place. If it is on homodiatomic molecules, like same atoms. Heterodiatomic molecules, like different atoms, like that. Or if it is an atomic orbitals, n number of atomic orbitals, if it is takes place in the linear combination of the atomic orbital, method. So LCAO means linear combination of atomic orbital. So n number of atomic orbitals, if it is mixing takes place in the linear combination of atomic orbitals, equal number of molecular orbitals are generated. If two atomic orbitals mixing takes place, two molecular orbitals are generated. Right? And these molecular orbitals will be resulted from the addition method, from the addition of these atomic orbitals. Addition takes place. The generated molecular orbitals, which are called as the bonding molecular orbitals. And the molecular orbitals resulting from the anti-bonding atomic orbitals, by using the subtraction or destructive method, additive or constructive, subtraction or destructive manner. If it is in the destructive manner, as a subtraction manner, if it is takes place, the resulting molecular orbitals, which is considered as the anti-bonding molecular orbitals. Those molecular orbitals cannot involve in the bonding, that is called as the non-bonding molecular orbitals. Not involved in the bonding, that means like lone pair electrons. If it is not participated in the bonding, that is considered as the non-bonding molecular orbitals. Based on the energy, anti-bonding molecular orbitals energy will be high compared to the bonding molecular orbitals. In between these two, non-bonding molecular orbitals are there. So bonding molecular orbitals energy is less and it may be more stable, like that, because the electrons which is present in the bonding and molecular orbital, that is considered as somewhat stable. If it is the electrons which is more number of electrons, if it is present on the anti-bonding molecular orbital compared to this bonding, suppose sometimes it may be considered as an unstable. Right? So bonding molecular orbital is first filled, later it may be anti-bonding molecular orbital. Like before that, so based on the energy, bonding molecular orbital energy is more than the anti-bonding molecular orbital. Bonding molecular orbital energy is less. Lowest energy. This is an highest energy. Which one is more energy? Anti-bonding molecular orbital energy is more. Anti-bonding energy is more. Bonding molecular orbital is less than to the non-bonding. This is less than to the anti-bonding. Anti-bonding is more. Right? Now, anti-bonding molecular orbital energy is more. So in UV like spectroscopy's point of view, the transitions also takes place from bonding to anti-bonding, like that. So left it that. And also sometimes it may be in the term symbols point of view also, or electronic transitions in the like that electronic spectroscopy point of view. So sigma bonding and pi bonding, sigma star as well as the pi star anti-bonding molecular orbitals are there. If it is not involved in the bonding, lone pair of electrons like n, it may be mentioned, small n. Right, number of lone pairs, based on that n it may be there. Sigma, pi, sigma star, pi star, and this is non-bonding. And sigma and pi sigma is gerade, pi is ungerade, and pi star is gerade, sigma star is ungerade, based on the center of inversion or center of symmetry. Based on center of inversion, if it is present, that is considered as the gerade. If it is not there, that is considered as the ungerade. Right? So I can explain in the electronic spectroscopy point of view, the electronic transitions possible based on the selection rules. Based on the selection rules, gerade to gerade or ungerade to gerade, which one it may be takes place, which one it may be possible, and bonding to antibonding or antibonding to bonding, which one it may be, selection rules is there, electronic transition. That is explained in the electronic spectroscopy point of view. We can discussion takes place. That means in the electron transition means promotion of the electron or shifting of the electron from one molecular orbital to another molecular orbital. That is called as the electronic transition. That's simply. Now, leave it there. So, in the molecular orbital theory case, in the linear combination of the atomic orbital method, bonding molecular orbitals are generated as well as the antibonding molecular orbitals are generated first. So, according to that molecular orbital concept, molecular orbital theory concept, first, whatever the molecular orbital which is having lowest energy, the molecular orbital which is having lowest energy is filled first. Lowest energy is filled first. So that means which one is filled first? Bonding molecular orbital is filled first. Non-bonding means which is not involved in the bonding. Already lone pairs are there. So next again, which one is level is filled? Anti-bonding molecular orbitals. Bonding, after then anti-bonding is filled. Right? So molecular orbital having lowest energy is filled first. Second one concept. Second one, any molecular orbital, whatever the molecular orbital you can take, right? Or in each molecular orbital, each molecular orbital, the filling of the electrons takes place in each molecular orbital cannot exceed 2 electrons, filling of the electrons in each molecular orbital, or the maximum number of electrons in a molecular orbital, whatever it may be, you can consider, right? The maximum number of electrons in each molecular orbital, whatever the molecular orbital you can take, cannot exceed 2. Cannot exceed 2. Cannot exceed 2 means how many electrons are there? 2 electrons are only. Maximum number of electrons filled in a molecular orbital, how many is there? 2. That cannot exceed. Is maximum number is 2. That means it may be 1, it may be possible, or 2, it may be possible, or it may be empty also there. Cannot exceed 2. Cannot exceed 2. And the 2 electrons also with of opposite spin. The 2 electrons also with opposite spin. 2 electrons also with opposite spin. That means one is plus half clockwise direction, another one is anti-clockwise direction minus half. Right, in the downward direction. Upward direction is plus half, downward direction is minus half. Right, this is plus half, this is minus half. This is plus half. Maximum number of electrons in each molecular orbital cannot exceed 2. That is the second statement. And third one, according to that molecular orbital theory, based on the filling of the electrons, if there are 2 degenerate molecular orbitals means having their energy will be same. Suppose for if it is going on takes place in the homodiatomic molecules like that molecule, pi 2px, pi 2py. Sometimes it may be given pi 2px, pi 2py we can obtain. That pi 2px, pi 2py, it may be same energy level, same energy bonding molecular orbitals. So same energy means having, that is considered as a degenerate. If the 2 degenerate molecular orbitals are there, if it is 2 degenerate molecular orbitals are present, filling of electrons in each level, first 1 electron, in each level 1 electron, first 1 electron. After then pairing takes place. After then pairing takes place. First each level is one electron. If there are two degenerate degenerate levels are there, these two are the degenerate levels. This suppose pi 2px, pi 2py if it is there. There are two electrons are there, suppose each one level is filled one electron first. Later again it may be filling, pairing takes place. So first which one it may be there? Each one level one electron. Each one level one electron. There are two degenerate molecular orbitals are there. Pairing of electrons will occur. Pairing of electrons will occur. First each one is filled with one electron. First each one is filled with one electron. Then pairing of the electrons will occur. Right. So one is molecular orbital having lowest energy is filled first. Next, in each molecular orbital the number of electrons is filled is not exceeding 2. That means maximum number it may be 2. With having opposite spins, one is clockwise, another one is, that means one is plus half, another one is minus half, downward and upward direction. If there are two degenerate molecular orbitals, either bonding or anti-bonding if it is there, there are two degenerate molecular orbitals. First each one molecular orbital having filled with one electron, then pairing takes place, then starts the pairing. Now another one which is bond order. So the bond order which is directly proportional to the strength of the bond. Bond order is directly proportional to the strength of the bond. Strength of bond. So bond order is directly proportional to the strength of the bond. That means if more bond order is there, that bond having more strength. Bond order is more bond strength. So suppose bond order it may be 1, 2, 3, it may be, suppose it may be obtained, that it may be considered as the single bond, 2 it may be there double bond, 3 it may be there triple bond, like that based on the bond orders. 1 it may be single bond, 2 it may be double bond, and 3 it may be triple bond. That means triple bond is more stronger than the double bond, than the single bond. So that's why bond order is considered as the strength of the bond, is directly proportional to the strength of the bond. And bond order is more and strength of the bond is more. When strength of the bond is more, that means if it is for the cleavage of the bond, that means bond dissociation energy also more. Required bond dissociation energy also more. Bond dissociation energy also more. Bond dissociation energy also more. So that means bond order is directly proportional to the strength of the bond as well as the bond dissociation energy. And another one linkage also it may be takes place. I can explain. When bond strength is more, bond strength is more means bond length is less, more attractions will be there. So bond strength is more, what will be happen? Bond strength is more, bond length is less. Lower the bond length, stronger the bond. Bond length it may be more, attractions will be weak, so it may be easily dissociation takes place, less bond dissociation energy is required, and that is weak bond, as well as that bond length is also more. Bond length is more, weak bond. That is bond order is also less, as well as the less bond dissociation energy is required. That means bond order is related with the strength of the bond. Bond order is related with the strength of the bond. That means it's directly proportional to the more bond order, more strength of the bond. Bond strength is more, to cleave the bonds, more energy is required. So that's why bond dissociation energy also more for the stronger the bond or strength of the bond, or bond order is more. Then bond length it may be less. Bond length it may be less. So now what is the bond order? How this bond order it may be an important one, it may be there, so it may be played an important role. So what is bond order? How can you calculate the bond order? Bond order is equal, there is a principle which will be proposed. Bond order is equal half to the, it may be half to the difference between the difference between the number of bonding molecular orbital electrons minus number of anti-bonding molecular orbital electrons, NB minus NA, half to the NB minus NA. So what is happening? Number of bonding electrons as well as the number of anti-bonding electrons to half half to the difference between the number of bonding as well as number of anti-bonding electrons. NB is what? Number of bonding electrons. Number of bonding electrons means bonding molecular orbital electrons. And Na means number of anti-bonding molecular orbital electrons. Anti-bonding molecular orbitals electrons. Anti-bonding molecular orbital electrons, right? So this one, by using this, we can calculate the bond order. If it is bond order is 1, single bond. Bond order is 2, double bond. Bond order is 3, triple bond. Right? So I can mention like bond order is 1, single, 2, double bond, 3 is triple bond. Right? Now based on this, for suppose we can calculate the homonuclear diatomic molecules in case of homonuclear diatomic molecules. In case of homonuclear diatomic molecules, what will be happen? Homonuclear diatomic molecules case, right? Two such type of similar molecules are there. That means their atomic orbitals energies will be similarly or approximately same. Atomic orbitals having same energy is there. Atomic orbitals having same or similar energy is there. If it is in homonuclear diatomic molecules. Homonuclear diatomic molecules. So if it is in heteronuclear diatomic molecules, hetero case what will happen? So atomic orbitals it may be different. That means suppose CO is there, carbon and oxygen it may be different strengths will be there. Different strengths. So that's what the atomic orbital energy is also not same as well as the carbon as well as the oxygen like that. So but in the case of the homonuclear diatomic molecules, suppose H2, N2, O2 like that, both are having similar atoms. So that's what having same energy it may be there. In the molecular orbital energy level diagram also having same energy is there. Having same energy is there. First one, suppose we can see for the homonuclear diatomic molecules. Homonuclear diatomic molecules. Homonuclear diatomic molecules. In homonuclear diatomic molecules, how can you calculate? In case of the homonuclear diatomic molecules, suppose in case of the homonuclear diatomic molecules, suppose we have seen the homonuclear diatomic molecules of the first and second row elements of the first as well as the second row elements in periodic table. In periodic table, first and second row elements. First as well as the second row elements of the periodic table we have considered for the homonuclear diatomic molecules generalized purpose. So for that purpose, in the first row of elements H2. In first row we can take H2. So in H2, how many electrons are there? H case 1 electron and another one hydrogen 1 electron. Hydrogen atom 1 electron, another one hydrogen atom 1 electron. 2 atoms are there. 2 atoms, how many electrons are there? 2 atoms, 2 electrons are there. 2 atoms, 2 electrons. These 2 electrons can be filled, right? These 2 electrons can be filled. Sigma 1s2, sigma is bonding. Sigma is bonding. And sigma star, next immediate one is sigma star anti-bonding molecular orbital, that is 0. Sigma is bonding and pi is bonding. Sigma as well as pi is bonding due to that overlapping, right? And additive method like that. So pi star and sigma star is anti-bonding molecular orbitals. While consider the atomic in the first row, second row case, what we have to consider? Suppose 1s, 2s, 2p, like 3s, that type of atomic orbitals we are considering, right? 1s, 2s, 2p like that, 3s, 3p like that, right? So now here it is 1s atomic orbitals which are there in the H2 molecule. So 2 atoms are there, 2 electrons are there. Each one atom, 1 electron, 2 atoms, 2 electrons. The 2 atoms, that it may be sharing takes place, bonding it may be formation takes place. So the 2 electrons are filled in the which level? Bonding level first. Bonding is level. Compared to the anti-bonding, bonding is lower energy level. First, these two electrons are filled in the bonding level. Bonding level. So sigma 1s2 and sigma star 0. So now here it is. Bond order is how much? Bond order is equal half into number of bonding electrons. How many bonding electrons are there? Sigma 1s is bonding 2 electrons. Anti-bonding is how many electrons? 0. Sigma star is anti-bonding. How many electrons? 0. So how much is the bond order? 1. Bond order is equal 1. Bond order is equal to 1. That means in H2 molecule, so between the H and H atoms, which one bond formation takes place? Single bond, right? So that means bond formation takes place. That bond order is 1. That bond it may be considered as an which bond? Single bond between the H2 molecule. Now another one more. In the bond dissociation energy of the H2 molecule, bond dissociation energy of H2 molecule is 458 kilojoule per mole. 458 kilojoule per mole or kilojoule mole inverse, the bond dissociation energy, as well as the bond length between the H2 two hydrogen atoms, bond length of H2 molecule. Bond length of H2 molecule or between the two hydrogen atoms is 0.74. Is 0.74 angstroms. Is 0.74 what angstroms? 0.74 angstroms. Next, suppose in another one example of the homonuclear diatomic molecule case, H2 molecule. H2 plus molecule. H2 plus. In H2 plus, how many electrons are there? 1 electron only. Because H2 molecule, each one hydrogen atom having 1 electron. But H2 plus charge is indicates to loss of 1 electron. Plus 1 it is there, 1 electron. Plus 2 is there, 2 electrons is losing. So total how many electrons? 1 electron here in this case. After losing 1 electron is remaining. So what is the electronic configuration is what? Sigma 1s1. Electronic configuration is sigma 1s1. Sigma star 1s0. Sigma star 1s0. Now bond order is how much? Half into number of bonding electrons 1 and anti-bonding is 0. That means how much bond order is? 1/2 or 0.1. So now here in this case bond order is 1/2 or 0.5. The bond it may be existing or not. There is a question which is there. The bond it may be existing or not. So when the bond order is positive, bond is existing. Bond exists between the molecule, between the hydrogen atom. Bond is existing. When bond order is positive, bond is existing. But compared to the H2 molecule, H2 plus is less stable. Compared to H2 plus is less stable. Compared to H2 plus is less stable. So bond order is also less compared to the H2 plus bond order is less, right? And H2 plus is less stable. That means H2 is more stable than H2 plus. And H2 plus case, the bond dissociation energy 269 kilojoule per mole. The bond dissociation energy is 269 kilojoule per mole. That means more bond dissociation energy is there in case of the H2 molecule, right? That means bond dissociation energy, required bond dissociation energy is more. That means bond strength is also more. So now here it is bond dissociation energy is less, bond strength is also less. So easily bond cleavage takes place compared to that H2 molecule. H2 plus ion case, easily bond dissociation takes place. So how much it may be takes place? Bond dissociation energy is 269 kilojoule per mole. When bond length is how much? Bond length, it may be compared to the H2 molecule, the bond length it may be more or less, bond length it may be more. Why? Because it is weaker bond. Easily dissociation takes place. So bond length is less, that is stronger bond. Bond length is more, that is weaker bond. So this is 0.74, this is how much? 1.04. This is H2 and H2 plus ion case, suppose. And another one homonuclear diatomic molecule of the first row element, H2, the helium 2 He2, hydrogen and helium in the first row, 2 atoms are there in the periodic table. So helium 2, what will happen? Helium 2 molecule, what will be happen? Now, in case of helium 2 molecule, how many electrons are there? Helium is 2 electrons, in the atomic number is 2 electrons, and 2 helium atoms are there. Total how many electrons? 4 electrons. 2 helium atoms, 4 electrons are there. 2 helium atoms. For each helium atom 2, and 2 helium atoms are 4 electrons. Right? Now, so what is the electronic configuration is sigma 1s2 and sigma star 1s2. 2 electrons are filled in the bonding level sigma first, later another 2 electrons in the anti-bonding level, like this. 1s of 1 helium atom, another 1 helium atom of 1s. So in the bonding case, sigma 1s2, in the anti-bonding case, sigma star 1s2, like this. This type of diagram it may be there. Suppose we go for the diagram, but it may be not necessary here in this particular point of view, the diagram. So sigma 1s2 and sigma star 1s2. This is bonding, this is anti-bonding. So bond order is how much? Half into bonding molecular orbitals are 2, bonding molecular orbital electrons are 2, anti-bonding electrons are also 2, number of bonding electrons are 2, anti-bonding electrons are 2. Now here in this case, what will happen? 2 minus 2 is 0. That bond order is how much? 0. Bond order is 0. When bond order is 0, that molecule is not existing. Bond order is 0. The molecule not exist. That means not stable. The molecule not exist. It is not stable. And sometimes, which is in the examination point of one of the examination point of view, in helium 2 bond order is 0, the molecule is not existing. Why it is? Sometimes it may be mentioned. So that means the anti-bonding molecular orbitals are anti-bonding effect in helium 2 molecule, anti-bonding effect of anti-bonding molecular orbitals, anti-bonding molecular orbitals is more, anti-bonding effect is more compared to the bonding molecular orbitals, Anti-bonding effect of anti-bonding molecular orbitals is more compared to the bonding molecular orbital. That means if it is more number of electrons, it may be there, or it may be equal, it may be there. Anti-bonding strength is more, suppose that molecule is not existing. Anti-bonding effect of anti-bonding molecular orbital is more compared to the bonding molecular orbital, so that this molecule which is not exist, and bond order it may be 0. This is for which case? Helium 2 case. Helium 2 molecule. Next, another one molecule, if it is this second row element we have seen, suppose the second row elements. So in the second row elements case, which one molecules are there in the second row elements? Second row of the periodic table. Lithium 2 it may be there, beryllium 2 and boron 2, C2, N2, O2 and F2. Right? That elements are there in the second row in the periodic table. You know that periodic table very well, so that's what I am not interested to write the periodic table, because it is a basic one. Everyone knows periodic table. The rows and columns in the periodic table you are very well known. So that's what, again, this is not, here it is. I cannot mention, I cannot write this total table, I cannot draw. So now here it is, which one it may be there? Second row elements of the periodic table. So that means here it is lithium 2. So lithium 2, one lithium is how many electrons? One lithium atom is how many electrons? 3 electrons. So 1s2 and 2s1 is there. So another one lithium electron is also there. So total is how many electrons? 2 lithium atoms is there. So total is how many electrons? 6 electrons. 6 electrons. Now in this lithium atom case, I can write the electronic configuration, lithium 2 case, lithium 2 molecule case, electronic configuration of the filling of the molecular orbitals. So I can mention this sigma 1s2, total 6 electrons. So sigma star 1s2 and sigma 2s2. 2s is also there, sigma 2s2. Or in second row elements, in all second row elements, this sigma 1s2 and sigma star 1s2 is filled. Sigma 1s2 and sigma star 1s2 is filled because 6, 7, 8, 9 that electrons will be there. So this one is filled, more than 4 it may be there. So this 4 electrons is there, this one is filled. When this is filled, the inner cells will be filled compared to the 2s. This 1s is considered as an inner cell. 1s is considered as the inner cells. These inner cells, these filled inner cells, 1s is inner cells. Filled inner cells can be shown or can be designated with symbols KK. Can be designated with the symbols KK. One inner cell, another one inner cell, KK. So that's what, this is unperturbed. That means it's not changed. These levels are not changed for second row of elements. So that's what the inner cells are filled, these values are not changed. So unperturbed. So that's what I can mention this electronic configuration KK into, right, sigma 2s2. Sigma 2s2 or sigma 1s2, sigma 2s2, sigma 1s2, sigma star 1s2, sigma 2s2. Anyone you can write. So out of these two, any configuration it may be given. So if we can take this one, suppose this one, half into number of bonding levels are how much? How much is there? Bonding is these two and this one is 2. How many is there total? 4. Anti-bonding is 2. How much it may be there? 2 by 2 is 1. Or this one is considered, suppose this bond order is how much? Half into number of bonding is 2, anti-bonding is 0. If you have to consider this configuration, KK, inner cells are filled. So what will happen? 2 by 2. That means how much it may be there? Bond order is 1. So the bond order is not unperturbed. So it may be unperturbed. It may be not changed. It may be not changed, unperturbed. So KK cells will be filled. Like this one you can use complete or this one you can write. So whatever it may be, same. Right? In this lithium 2 molecule. So lithium 2 molecule. If you can consider this, what will happen? This anti-bonding molecular orbital is an empty. If you can consider this KK, anti-bonding molecular orbital is empty. Anti-bonding molecular orbital is empty. And this bond order is 1. What will happen? Sigma bond is there. Bond order is 1. Sigma bond is present. And the bond dissociation energy is 105 kilojoule mole, kilojoule for mole or kilojoule mole inverse. So the bond length is also nearly 2.07 angstroms it may be there. 2.67, sorry, not 07. The bond length it may be 2.67 angstroms. 2.67 angstroms which is there. This is for the lithium 2 molecule. Right, that it may be that the bond length, bond dissociation energy, the values are not necessary, but sometimes it may be comparison takes place. If it is which one bond dissociation energy is more, comparison between the two molecules, bond dissociation energy is more, that is more stable, like that. So another one it may be C2 case, beryllium 2 case. So in beryllium 2, so total is how many electrons which is there? Beryllium is 4, another one beryllium is 4, total is 8 electrons. That inner cells are filled, that means 4 electrons, sigma 1s2, sigma star 1s2, 4 is left. Another how many is there? Sigma 2s2, sigma star 2s2. Total is how many electrons? 8 electrons. Each one beryllium atom having 4 electrons. This KK means 4 electrons is completed. Sigma inner cells are completed. Sigma 1s2, sigma star 1s2 inner cells. right? That is filled inner shells which is there. So sigma 2s2, sigma star 2s2. So that means what will be happen? Bond order is equal to 1. How much bond order is equal? Half into number of bonding is 2, anti-bonding is 2. That means what will be happen? 0. When bond order is 0, what will be happen? The molecule is not exist. Molecule not exist. Molecule not exist. Next, after beryllium, which one is there? Boron 2, B2 molecule. In B2 molecule, next example is B2 molecule. Next, in B2 molecule, how much is there? So 5 electrons. Boron is 5 atomic number. So 5 electrons are there. Total how many electrons are there? Total is 10 electrons. So out of the total 10, this is KK. That means which one it may be there? These shells will be filled. K shell will be filled. That means 4 electrons are filled. How many is left? 6 electrons. How many is left? 6 electrons. That 6 electrons is filled. Sigma 2s2, sigma 2s2, and sigma star 2s2. How many is completed? This is 4, 1s2, sigma star 1s2, and 2s2, sigma star 2s2. 8 is completed. Another 2 electrons are there. The 2 electrons are designated as, which is present in the degenerate pi levels of 2px1 and 2py1. I mentioned very beginning, if 2 are degenerate energy levels, 2 are degenerate molecular orbitals are there, in each one level, one electron is first filled. These 2 are degenerate having same energy level. So pi 2px is equal pi 2py. Actually pi 2px is equal pi 2py. So that's why these 2 are degenerate levels. So that's what one electron is filled in these 2 levels. Pi 2px is equal pi 2py. Sometimes it may be mentioned, right? 2px is equal 2py also, right? Or pi 2px, pi 2py. One electron is filled. Now here in this case, what is the bond order? Half into, how much is there? How many bonding electrons? 4, and anti-bonding electrons are 2. So that means which one is there? 2 by 2. 2 by 2. That means 1. Bond order is 1. 4 minus 2 by 2 is bond order is 1. When bond order is 1, which one it may be there? Single bond is existing between the B2 molecule. Single bond is existing between the B2 molecule, and nearly that bond dissociation energy is 289 kilojoule for mole. Kilojoule for mole, 289 it may be there, and bond length is also nearly 1.59 angstroms it may be there, but it may be not necessary in all these cases. And suppose it may be there C2 case. After B2, which one it may be there? C2. In C2 case, what will be happen? C2 molecule. So in C2 carbon, how many? What is the atomic number? 6. That means total how many electrons are there? 12 electrons for the C2 molecule. Each one carbon having 6 electrons. Total C2 is 12 electrons. So the 12 electrons, KK, this shell will be filled. This shell will be over. What is that? This shell will be over. So when this shell will be over, so 4 electrons are over. Next, how many electrons is left? 8 electrons. That means sigma 2s2, sigma star 2s2. Next, pi 2px 1 and pi 2py1. Next, pi 2px2. Another 1 electron is also filled in these 2 levels. First 1 is filled, again 1 it may be there. This is 4 is completed, sigma 1s2, sigma star 1s2. Next, how many is there? 8. This 8 will be filled like this. Now, bond order is how much? Half into, how many bonding molecular orbital electrons? 6 in this particular case. These 2, this one 2, 2, 6, and this is 2. How many is there? 4 by 2. That means 2. Bond order is 2. Bond order is how much? 2. When bond order is 2 here in this case, bond order is 2. What will be happen here in this case? CC double bond which is there. CC double bond which is there. Bond order is 2 means CC double bond which is there, and their bond dissociation energy also nearly 689 something value is there, 699 kilojoule per mole. Bond dissociation energy also, 629 kilojoule per mole. Bond dissociation energy is 629 nearly. Bond dissociation energy is how much? 629 kilojoule per mole. So in case of B2 is nearly 289, 280 something it may be there. That means compared to the C2, B2, C2 is having more bond dissociation energy and more stable. And bond length is, bond order is also how much in case of B2? 1. In case of C2 is 2. Bond order is more bond strength. That means compared to the B2 boron, C2 is more stable. C2 is more stable, and their bond dissociation energy also having more, and bond length is less compared to the B2. Bond length is less and bond dissociation energy is more, right, compared to the B2, right? And double bond is existing, and also double bond is existing, and there is no lone pair electrons, in this particular level, in anti-bonding level. There is no lone pair electrons in that levels. There is no lone pair electrons. One electron is not there. All are paired. So that's what C2 is also considered as an which one? Diamagnetic. C2 is considered as an which one? Diamagnetic. C2 is diamagnetic. Why? Because all bonding are, all levels are filled. All are filled. Lone pair electron is not present. Next one, it may be N2 molecule. In the second, another one, it may be in the second row elements of the periodic table, homonuclear diatomic molecules case N2. So one nitrogen atom is how many electrons are there? 7 electrons. One nitrogen atom means 7 electrons. Total is how many electrons? To one nitrogen atomic number is 7 electrons. Total is how many electrons? 14 electrons. Out of these 14, inner shell is filled, that means 4 electrons are completed in the KK, sigma 1s2, sigma star 1s2. Now, which one it may be there? Sigma 2s2, sigma star 2s2. How much is completed? 8 is completed. Next, pi 2p x2, pi 2p y2. How many is completed? This one is completed, 12. This one, up to this it may be same, 12 it may be completed. If 12 is completed, again how many electrons is addition? 2 electrons. For this one is 2 electrons is addition. When 2 electrons is addition, each one case it may be 2 electrons is addition takes place for this each one row case. Lithium 2 to the beryllium 2, 2 to boron 2, and C2, each one case 2 electrons addition takes place. So this one is also compared to this 2 electrons addition takes place. The 2 electrons which is present in the sigma 2p Z2, sigma 2p Z2, the 2 electrons will be present in the which one level? So that level will be sigma 2, that level will be present in the sigma 2p Z2, sigma 2p Z2. Right. So here it is in the N2 molecule. What will happen? More number of bonding molecular orbitals are there compared to this, right? Compared to this C2, more number of bonding electrons are there. Bonding electrons are more, and compared to this B2 molecule, C2 molecule. So bond order is equal half into number of bonding electrons are how many? 10. Here in 8. In this particular case, 6 to 8, and anti-bonding is 2. That means how much is there? 6 by 2. That means how much is there? 3. When bond order is 3, in N2 molecule, which one is existing? Triple bond is existing. Why? Because triple bond is existing, bond order is 3. Bond order is 3. When bond order is 3 in the N2 molecule, triple bond is existing. Triple bond is existing in the molecule, and bond dissociation energy is nearly 925 kilojoule per mole. 925 kilojoule per mole. So that means 925 kilojoule mole inverse. And bond length is 1.10 angstroms. 1.10 angstroms. That means, so compared to the C2, bond dissociation energy is more, and more number of bonding molecular orbitals, bonding electrons are there. So that's what we can say that. So compared to the C2, N2 is more stable. N2 is more stable and is also perfectly diamagnetic because there is no unpaired electron. This is also perfectly diamagnetic. If there is no unpaired electron which is not there, that is considered as the diamagnetic. Unpaired electron is not there, that is considered as which one? Diamagnetic. Next, another one which is O2 molecule, O2, oxygen, right? O2 case, what will be happen? O2. Oxygen, and another one it may be the F2 is there, O2 and F2 is there, right? Next is which one? O2 molecule. In the second row case, another one after N2, O2 is there. N2 is 14 electron. O2 is how many electrons? 16 electrons. Oxygen atomic number is 8. 8 electrons are there. 2 oxygen atoms are there. Total it may be 16 electrons. So that 16 electrons, 4 electrons is sigma 1s2, sigma star 1s2 is completed in the KK cells, inner cells. And sigma 2s2, sigma star 2s2. Now here in this case, while in the N2 molecule, after sigma 2s, sigma star 2s2, we are considering this pi 2px, pi 2py. Now here in this case, so after that sigma 2pz is there. That sigma 2pz can be written here in this case. The experimental results can be shown that sigma 2pz it may be less energy compared in this O2 molecule like that. So sigma 2pz2. And after that what we have to write? Sigma 2px2, sigma 2py2. Sorry, pi 2px2, pi 2py2, sigma 2pz2. So this configuration it may be slightly different compared to that N2 molecule. Up to that N2, this is the order is followed like that. After sigma star 2s2, pi 2px, pi 2py like that. After N2, this type of order it may be there. Sigma 2pz2, pi 2px, pi 2py2. So this is like the earlier one up to that. So this is 14 electrons is completed after like this. Next another one it may be sigma star, sorry, pi star 2px1 and pi star 2py1 it may be there. Pi star 2px1, pi star 2py1. So that means it may be less than also you have to write. This is energy order also it may be less than. That means this is highest energy compared to these levels. Increasing order we are maintaining. Right, so this is pi 2px2, pi 2py2 and pi star 2px1, pi star 2py1 it may be there. Now how many of the bonding and how many of the anti-bonding is there? So bond order is equal half into, how many of them is bonding? 4, this is 6 it may be bonding, sorry 6 not 6, 8, this 3, 6 and 2, 8 minus, how many is anti-bonding? 4. So due to that 4 anti-bonding molecular orbital electrons, 4 anti-bonding molecular orbital electrons, 4 anti-bonding molecular orbital electrons, this O2 is less stable, O2 is less stable than N2. O2 is less stable than N2. Which one? Because of 4 anti-bonding molecular orbital electrons are there. So in N2 case how many is there? 2 is there, 2 anti-bonding electrons. But in case of the O2 case 4 is there. Due to that anti-bonding effect will be increasing. When anti-bonding effect is more, that is less stable than the N2. When it is less stable than the N2 and the bond dissociation energy, so this bond dissociation energy here it is also nearly 496 it may be there, 496.4 kilojoule mole inverse or kilojoule for mole. So compared to the N2 is how much is there? Nearly 945 it may be there. So this O2 is how much is there? 496. That means compared to that N2, bond dissociation energy is also less, and bond length is also 1.21 angstroms. So bond length is more compared to that N2 molecule. N2 is 1.10. Now in the O2 case 1.21. Now half into this is how many? 4. That means how much it may be there? 2. Bond order is equal to, that means which one it may be there? Double bond is existing. Bond order is 2 means double bond. Bond order is 1, single bond. Although double bond is existing, the important one it may be there, this O2 is paramagnetic in nature. O2 is which one? Paramagnetic. O2 is paramagnetic in nature. Why? Because O2 is in paramagnetic. Why? Because O2 is in paramagnetic. See, listen, why? Because, so here, which one electrons are there? One electron which is there. So it may be lone pair electron is there. Lone pair electron is available. Lone pair of electron is available. So lone pair of electron is available in pi 2px1 and pi 2py1, not pairing. Only one electron. Lone pair of electron is available in antibonding molecular orbitals. Lone pair of electrons present in the antibonding molecular orbitals. So due to that, even though bond order is 2 is a even number, but it is a paramagnetic in nature. It is a paramagnetic in nature. So the another one more, the last one, it may be suppose F2 it may be there in case of F2, and in case of Ne2. Right? On that 2 is there F2 and Ne2. In case of F2 is what will be happen? F2 molecule. In case of F2 molecule. So atomic number is 9. 2 atoms will be there. So how many electrons? Total 18 electrons. So in addition to that, oxygen 16 electrons, 2 electrons will be added. 18 electrons. So which one is the electronic configuration? This is 4 electrons is completed. So sigma 2s2, sigma star 2s2, then sigma 2pz2, like the same one. So what will happen? Pi 2px2 is equal pi 2py2, then pi star 2px as well as the pi star 2py is there. Due to that, here it is 2 to 1 electron is there in this case. Here in addition to that O2 molecule, how many electrons? 2 electrons is addition. So that means which one it may be filled? Here in this case 2, and here in this case also 2 electrons which is there. Right? 2 electrons will be there. So there is no lone pair electron. There is no lone pair electron. So which one it may be there? It may be also considered as an diamagnetic. This it may be considered as an which one? Diamagnetic. There is no lone pair electrons. Now bond order is how much? Half into how many bonding it may be there? 4, 6, 8. Right? How many anti-bonding is there? 6 it may be there. So how much it may be there? 2 by 2. That bond order is how much? 1. So bond order is 1 means which one bond is existing? Single bond is existing. Single bond is existing. Now single bond is existing. Although single bond is existing, now compared to the N2 and compared to the O2, F2 is stable or not? F2 is less stable. F2 is less stable compared to O2 as well as N2. Compared to the O2 as well as N2. Why? Because compared to the O2 and N2 it is less stable. So how many antibonding electrons are there? 6 antibonding electrons are there. 6 antibonding molecular orbital electrons are available. So more antibonding effect is there. More antibonding effect. more antibonding effect it may be there. So that means not exceeding the bonding but more antibonding effect. So 6 electrons is present in the antibonding molecular orbital. Due to that, this F2 is less stable than O2 as well as N2. O2 as well as N2, it is less stable. And the bond dissociation energy compared to the O2 as well as N2, which is very less. So how much it may be there? Nearly 159 kilojoule per mole it may be there. Nearly, approximately that value is how much? 159 kilojoule per mole. Approximately 155 to 159 kilojoule for 159 or 155. Sometimes it may be mentioned in some of the books 155 approximately that value kilojoule for mole. This is the F2 molecule. And last another one it may be the Ne2. Neon. Ne2 molecule. How many electrons is there? 2 electrons to this. Neon is 10, so 2 neon atoms 20. That means this complete one it may be over. After that, which one it may be there? Sigma star 2pZ2. Sigma star sigma 2pZ2 is there. Sigma star 2pZ2 is there. So if it is increasing order takes place, suppose this one it may be right like this. This order is also it may be there. So the inner cells are filled. Sigma 2s2. Sigma star 2s2, and what will be happen? Sigma 2pz2 and pi 2px2 is equal pi 2py2, then pi star 2px2, then pi star 2py2. Up to this it may be same. After that, another one more it may be antibonding of the sigma star 2pz of 2. So in the earlier one is how many antibonding electrons? 6. But now here it is how many is there? Again 2 addition takes place. That means 8. So bond order is how much? Half into bonding is 8, antibonding is 8. Or you can consider with the KK, this inner cells also you have to consider. Suppose what will happen? This is 10, this is 10. Sigma 1s2 and sigma star 1s2. This is 10 and this is 10. How much total value is? 0. 10 it may be there, 10 minus 10 or 8 minus 8. You can ignore the KK levels. 10, 10. If you consider 8, 8. Bonding, antibonding. So bonding is bond order is 0. What will happen? Molecule is not exist. Molecule is not exist. This molecule is not exist. Right? So this is for the homonuclear diatomic molecules case. Homonuclear diatomic molecules. Next in another one case, we have seen similar one. Like we have seen the earlier one, homonuclear diatomic molecules of the first row, second row. Now the molecular orbital energy level diagram of MOID is molecular orbital energy level diagram of some of the heteronuclear diatomic molecules. Heteronuclear diatomic molecules. Molecular orbital energy level diagram. MOID is nothing but the molecular orbital energy level diagram of the heteronuclear diatomic molecules. First example it may be given CO, carbon monoxide, CO case. In CO, which one? Those two are different atoms, different atomic orbitals are there. Different atoms means different atomic orbitals, right? So carbon is how much it may be there? 1s2 and 2s2 and 2p2. 6 atomic number is 6, 1s2, 2s2, 2p2. And oxygen is what? 1s2, 2s2, 2p4. Because atomic number is 8. 2p4 is there. And that is 2p2. Right? And compared to the carbon, oxygen is more electronegative. Oxygen is more electronegative. Compared to the carbon, oxygen is more electronegative compared to the carbon. When oxygen is more negative, when which one? Compared to more electronegative compared to carbon. Compared to carbon, oxygen is more electronegative. When it is more electronegative, so the bonding molecular orbitals of, that means the atomic orbitals of, atomic orbitals of oxygen. So if it is an heteronuclear diatomic molecules, both carbon and oxygen atomic orbitals not in same energy, not in same energy level, not in same energy, or nearer, not in closer energy. So because oxygen is more electronegative, that means the atomic orbitals having also different energy, in energy level diagram having different energies. That means one is lower energy, one is higher energy. Whatever that lower energy atomic orbitals are there, that is the oxygen case. Oxygen atomic orbitals of oxygen having lower energy, than carbon. Right? So total is how many electrons? This is 6 electrons and this is 8 electrons. 6 plus 18 is how many electrons? Total is 14 electrons are there. Or if you can see the energy level diagram of the carbon, and this is oxygen. Carbon as well as the oxygen case. Energy level diagram of the carbon as well as oxygen. So if we can ignore the ground level, Kk energy level, so total is 14 electrons are there. So which one it may be there? Sigma 2s2, sigma star 2s2, and pi 2px2, that is equal pi 2py2. How many is completed? 4 plus 8, 12 is completed. So another one it may be the pi star 2px is equal 1 and pi star 2py 1 is there. Pi star 2px 1. Sorry. After that, not pi star. What is happening? Sigma 2pz is also there. After this, sigma 2pz. 14 or below 14. This type of configuration is there. Electrons. Sigma 2pz2. So this is over. 8, 10, 14 it may be there. Right? Now, in the carbon case, which one is there? So you can exclude the outer shell, suppose Kk shell if you can exclude, which one it may be the inner cells which will be exclude. So you can consider this 2s2, 2p2, 2s2, 2p4 suppose. So carbon atom case, suppose which you can consider 2s2 of the carbon, and here it is oxygen having lower energy. So this is what oxygen of the 2s2. Oxygen of the 2s2, right, which is having lower energy. So now here it is this energy level, and this one if it is takes place, sigma 2s2, this is bonding, sigma 2s2. So how many electrons? 2 electrons, and these two are going to be form the sigma star 2s2, sigma 2s2 and sigma star 2s2. Now, why I cannot write these two are in the same energy level? The oxygen is more electronegative. Then this 2s2 atomic orbitals of the oxygen can be written as lower energy compared to that carbon is having higher energy. It is an energy axis like this. So this oxygen is having lower energy than this one. Now the bonding molecular orbital of oxygen, bonding molecular orbital which is closer to the oxygen, the bonding molecular orbitals are closer to the oxygen atomic orbitals, bonding molecular orbitals which is closer to the oxygen atomic orbitals. That's why the bonding molecular orbitals also possess more characteristics as that of the oxygen atomic orbitals possess, which is shown similar characteristics. Bonding molecular orbitals can show similar characteristics of that of the atomic orbitals of the oxygen, because which is very closer to that. And similarly, anti-bonding molecular orbitals are closer to the which one? Carbon atom. Anti-bonding molecular orbitals closer to the carbon atomic orbitals. And these anti-bonding molecular orbitals can be possess similar characteristics like that carbon. Next, another one level, which one level is there? Another one level, which one is there? Px is filled, Py is in the carbon atom, sorry, Px is 1, Py is 1, Pz is an empty, suppose. Because 2p2, this is 2p2, this level. 2p2. Next, another one, which one level is there here in this case? 2p4. Px is filled, Py is, Pz is 1 1 electron. Px, Py, Pz is 1 1 electron. Now here in this case also so this is in this case this orbitals of the which one it may be there, suppose. So I can write clearly, very clearly. Suppose P4, 2p2, this is 2 electrons, this is 2 electrons, Px, Py, Pz. And if you can see this, this is 2 electrons and this one is 2 electrons. These two and these two, it may be filling takes place, though this may consider as in which one? Pi 2px2 and pi 2py2, this configuration, pi 2px2, pi 2py2. Next, another one level is which one level it may be there? Another one, which one level? So this is sigma 2pz2. Pz2. Next, another one, which one level is there? Pi 2p, pi star 2px, pi star 2py. Next, which one level is there? Sigma star 2pz2. So bonding is only filled. This is an empty is there. Right. So now here in this case, what we can say that the bonding molecular orbitals which are having closer to the atomic orbitals of the oxygen atoms, anti-bonding molecular orbitals are closer to the atomic orbitals of the carbon atom. These are closer to the carbon atom. Right. In CO molecule. So now bond order is how much? In CO molecule, bond order is how much? Half into bonding is how many is there? 6 and 2, 8 it may be there. If you can compare with the KK shell, 10 is there, otherwise 8. And anti-bonding is how much? 2. That means 6 by 2, that is equal 3. Bond order is 3, what will happen? Triple bond is existing. Triple bond is existing. Bond order is 3, triple bond is existing between the CO. Which one is existing? Triple bond is existing. And bond dissociation energy is also more. Nearly 1069 kilojoule mole inverse is there. And bond length is less, nearly 1.14 angstroms. 1.14 angstroms. So this is which one case? CO molecule. This is CO molecule. Next, another one is similar one, it may be there, NO molecule. Another one, which one is there? NO molecule. NO case. Right, this is CO. Next one is NO, nitric oxide. And CO is diamagnetic or paramagnetic? Diamagnetic, because there is no unpaired electron. There is no unpaired electron, that is considered as a diamagnetic. Diamagnetic, there is no unpaired electron. Another one, it may be the NO. So this is atomic number is 7 and this is 8. Total how many electrons? 15 electrons. So if it is 15 electrons is there, so this inner shell is filled, 4 electrons is over, and sigma star 2s2, and if it is crossing more than 14 electrons is there, more than 14 electrons, you can go for this configuration, sigma 2pz2 and pi 2px2 and pi 2py2, pi 2px2 as well as pi 2py2. Another one is another electron which is present in the pi star 2px1. Pi star 2px1. Because 15 electrons are there. Only 15 electrons are there. So this one is less than like that, increasing order. Pi 2px1 is there. Now bond order is how much? Half into how many is there? 6 to 8 minus 3 is there. That means which one it may be there? 5 by 2, that is 2.5 or 2.5. 2.5 or 2.5 is the bond order. And due to the lone pair electron which is present in the antibonding molecular orbital, NO is less stable. NO is less stable than CO. NO is less stable than CO. And NO is which one? When antibonding molecular orbital electron is there, so that's why this is NO is considered as a paramagnetic, because unpaired electrons is there. Unpaired electron or lone pair of electron is there. Unpaired electron or lone pair electron is there. So that is considered as an which one? Lone pair, unpaired electron is there. So that one, that's why that is called, NO is called as an which one? Paramagnetic, because unpaired electron is there. Unpaired electron. Only one electron is there, unpaired electron. Right? Next, another one, which one the molecule you have to show? Last one molecule is HF. So compared to this earlier one, this HF molecule it may be different. This H it may be, which one it may be there? One electron is there, only solitarily single electron is there. Solitary single electron it may be there, 1s1. And F it may be how many is there? 9. So this is 1 electron plus 9 electron. Total is it may be there 10 electron. Right? So in this F it may be 9, 1s2, 2s2, 2p5 it may be there. 1s2, 2s2, 2p5. So now here in this case, this 1s electron it may be takes place, only 1s electron of the H, 1s electron of the 1H, and mixing takes place. In the 2p5 case, which one is there? 2px, 2py, 2pz. So one electron it may be there in the 2pz. That means 2pz electron or atomic orbital of the which one? 2pz atomic orbital of fluorine. 1s of the hydrogen atom and 2pz of the fluorine. Combination takes place, sigma bond formation takes place, sigma sp bond formation takes place, sigma sp bond formation takes place. Right, suppose you can see the H, only 1s electron is there. So in the hydrogen atom case, only 1s electron is there. In the fluorine case, which one is there? 1s2 is, you can left out, 2s2, 2p5 is there. 1s2 is, you can ignore that because that is a ground state kk level like that. So 2s2, 2p5 outer electron configuration, suppose you can consider. This is F case, 2s2. Another one level which is considered as an which one? 2p5. Another one which may be considered as an 2p5. 1s of the 1s1, it is 2p5. 2p5, right? Sigma, sorry, 2px2, y2 and z1 it may be there, right? Now here in this case, based on this, so these 2s2 is not involved in the bonding. So we can write in the energy level diagram f of, which one it may be there, 2s2, f of 2s2, f of 2s2 it may be mentioned, right? F of 2s2, f of 2s2 or 2s, right? Or 2s is mentioned. Next, another one case, the bonding, the hydrogen atom of the 1s, hydrogen atom of the 1s as well as this 2pz of the fluorine. Bonding formation takes place. Which one it may be there? Sigma sp, sigma sp2, sigma bond, sigma 2 sp. So sp bond formation takes place, sigma 2. This is bonding. And similarly, anti-bonding is formation takes place. Similarly, anti-bonding is there, sigma star sp, that is an empty bond. This is bonding, this is empty, anti-bonding. Now, this is over, 2pz as well as the 1s of the hydrogen atom as well as the 2pz of the fluorine, both are formation takes place. Now, another one it may be there, 2px, 2py is there, the 2px, 2py can be written as like this. F of, that means this is f of 2px, f of 2py, that levels will be there. 2px2, f of 2py2, right? That is non-bonding. This is not participated in the bonding. Lone pair electrons, these two lone pair electrons, this is one lone pair electron. These electrons will not participate in the bonding. Will not participate in the bonding. Only this unpaired electron of the 2pz and 1s both will participate in the bonding. Based on that, the electronic configuration, suppose you can see that sigma sp2, sigma kk shell, sigma sp2, sorry 2s2 and sigma sp2, 2s2, f2s2, sigma 2s, sigma 2 sp2 and f2px2, f2py2. So that means fluorine atom, or 2px2 and 2py2, and which one it may be there? Sigma star sp0, sigma star sp0. Right, this one is the configuration, 2s2, sigma sp2, and this is unpaired, right? Sorry, this is lone paired. These two are not participated in the bonding, non-bonding, and this one is there. Right? So we are considering only which one? This bonding and this anti-bonding. These are non-bonding levels. So based on this, this is bonding, this is anti-bonding. So which one it may be there? Bond order is equal half into how many bonding electrons are there? 2 electrons. How many anti-bonding electrons? 0. Because these are not participated in the bonding. Non-bonding, like that. So how many is there? Bond order is how much? 1. Bond order is 1. That means which one bond it may be existing? Single bond it may be existing. Which one bond? Single bond. Similar one it may be there in the case of the HCl also same. HCl also same, but the bond formation takes place 1s of the hydrogen as well as the 3pz of Cl. 3pz of the Cl. So which one it may be there? Sigma sp2, sigma star sp0. In case of the HCl, same bond order is 1. Bond order is 1. Remaining it may be non-bonding, it may be there, or it is not participated in the bonding. So this is for the HF molecule. HF molecule, this type of diagram it may be given for HF, heteronuclear diatomic molecules. So based on that, I will give one conclusion also. Sometimes it may be in examination point of view, detailed discussion if it is not mentioned. Suppose directly how can you say that? Whether it is paramagnetic or diamagnetic, how much is the bond order? Comparisons takes place sometimes. So one type of, generally we are using one type of chart it may be using. If bond order is, if it is number of electrons are 14, total number of electrons are 14. So you consider this bond order is 3. And if it is number of electrons, it may be increasing or decreasing takes place in addition to that 14. So if it is 13 is there, you can decrease half to that value. So here it is also half to end of bond order. So if it is 12 electrons is there and 16 electrons is there, this bond order is how much? 2. This bond order is also 2. If it is 16 electrons is there, bond order is 2. Although bond order is 2, this is in case of the O2 molecule paramagnetic. Why? Because paramagnetic, the unpaired electron present in which one? Unpaired electron present in antibonding molecular orbital. Unpaired electron is present, right? It is not paired. Only one electron is there. So if it is 11 and 17 is there, this bond order it may be 1.5. Or 1.5, or how much it may be there? 1.5. So it may be 10 and it may be 18, it may be there. This bond order is 1. And if it is 9 and 19 is there, this bond order is half. If it is 8 electrons are there, this bond order is 0. Molecule is not exist. So here it is also 20 is there, like Ne2 neon. So like this is Be2 beryllium. So this is Ne2 neon. Bond order is 0. Not exist. So sometimes it may be considered in this case half of the values it may be there, non-integer values. If it is integer values 1, 2, 3, it may be considered diamagnetic. Suppose integer it may be considered except 16. Integer if it is given, consider as an diamagnetic in most of the case. If it is non-integer it may be there, that means 1/2, 3/2, 5/2 like that it may be there. So if it is 1, 2, 3 like that integer it may be there. If non-integer it may be there, consider as which one? Paramagnetic. If integer is there, diamagnetic. So bond order it may be 1, 2, 3 like this, diamagnetic. Bond order it may be half, 3/2 like that it may be there, paramagnetic. Although 16, oxygen is having 16 electrons, bond order is an integer, but it is an paramagnetic. Why? Because it is a paramagnetic unpaired electron which is present in the antibonding molecular orbital, right?